Welcome to the last lecture for the course. We're going to look at Chapter 12, which is Analysis of Variance. So where we've been was we started looking at significance tests using testing one sample proportions, then we moved to two sample proportions, and in our last chapter in our chi-squared statistic, we're looking at three or more proportions that we're testing. Then we tested one mean, two means, either two sample or matched pairs, and now with analysis of variance, we're going to look at three or more means. So analysis of variance has been shortened into an ANOVA, and so we're looking for three or more population means, and we're testing that they're equal. So our null hypothesis will always state the number of means we have, that they're equal, and our alternative will always be at least one mean is different. You don't put not equal to's, you don't put greater thans, you don't put less thans. It's just at least one mean is different. When we do this, we're going to use an F distribution, and it's not symmetric. It's a little bit similar to our chi-squared distribution because it's skewed to the right. None of the values will be negative. 0 or positive are the possible values, and all the tests will be right-tailed tests. When we actually look at an ANOVA, the F statistic is the ratio between the variance between samples and the variance within samples. And we will have a numerator degree of freedom and a denominator degree of freedom. And that's how you find your critical values, and you can find those in table A5. But because we are going to concentrate on how to interpret the output from technology, we're not going to be doing much with that at all. And here's a picture of that F distribution. So again, ANOVA is a one-way analysis of variance. We look at them with one treatment or one factor. It's a characteristic that distinguishes our different populations. So in our chapter problem, we looked at blood lead level in children versus their IQ. So the treatment is going to be the lead level. Now, treatment was first used when ANOVA was developed because it was used in agricultural settings where they did treatments of fertilizer, different levels of fertilizer. Even though we talk about treatment, it isn't always imposed. So nobody went to these children that we're looking at and fed them lead to get them in one of the lead level groups or not. But we're only looking at one factor. There is also a two-way ANOVA, and a two-way ANOVA, you'd look at your individuals using two different factors, but we're not going to go there. We're going to simply focus on one-way ANOVA so that you are exposed to this type of test. If you ever have to carry out your own test, you will have taken more statistics classes, or you will have a statistics advisor. Again, we're going to emphasize interpreting the results from technology. Here's what has to happen. All of our populations have to be approximately normal. The populations need to have the same variance, and if they have the same variance, they have the same standard deviation. Again, it's very, very important that all of our samples are simple random samples, and our samples are independent. They're not matched in any way, and that they are characterized in only one way. As we said before, our appropriate null hypothesis is that every mean is equal. And so we're going to identify the p-value from our display, and then we're going to form a conclusion based on the following criterion. So again, p-value is less than alpha, we reject. If the p-value is greater than alpha, we fail to reject. This is no different than any of the other significance tests that we've done. Now, when you actually reject that null hypothesis, we are only saying that the means are not equal. And we would use further tests to see which of the specific means are not equal. Because this is an introductory course, we're not going to do those tests. We're going to do informal investigation of our results. So here is the data from the chapter problem. And so we have low blood level, medium blood level, high blood level. And we did a little preliminary descriptive statistics. And so we have the sample size, the mean, and the standard deviation for the 3 samples. We're going to look at the standard deviation, and they're all in the same magnitude. They're all in the teens. We don't have one that's 100 and one that's 1,000 and one that's in the ones. They're approximately the same. That's all we need to have. So the 3 samples appear to come from populations that are approximately normal. They have standard deviations that aren't dramatically different. We can treat the samples as simple random samples. They're independent of each other, and they are categorized to one single factor, that is lead level. In step 1, the 3 means are equal. Our alternative is at least one of the means is different. In step 2, we're going to set our significance level, and we're going to set that at 0.05. And then we're going to look at the technology on the next slides. And these are the outputs that we would get from StatDisk, from Excel. I want to talk about these just a little bit, in that our test statistic is the same. Our p-value is the same. And these, oops, sorry, that's not right. The p-value is the same. And these also show our critical F. That would be the number we would find from the table that would be the boundary of our rejection region. StatCrunch doesn't give us that, but we don't need it if we have the p-value. And here is our StatCrunch, and again you see the same F statistic, you see the same p-value. Here's F and P in Minitab, and go ahead and you would put your step 3, it's actually a step 3 and 4 combined for our 6-step test. And some more. Okay, so here we go. Our p-value is 2.0. That would be probably step 4. Here, this is going to be step 4. And we can reject our null hypothesis. That's going to be step 5. And then here we have step 6. Now, this is true. We can't conclude formally that any mean is different than the others. We are going to do it informally. So we've concluded that the means are not the same. And so we're going to go on and we're going to informally evaluate the different means. So let's look at our output from StatCrunch. And right here is where we are going to find our F statistic. And then right next to it we find our p-value. Now on the previous slides they said the p-value rounds to 0.02. but here it is out a few more decimal places. The thing I want to show you here is that here we have the means, and this is where we can look at this and we can do our informal investigation here, and it looks like low lead level, which is group 1, has a slightly higher IQ than the other two groups. And so we could say in our summary statement that it appears that the low lead level IQ is different than the other two levels. But to say that formally, we would have to do more tests. Our ANOVA is always right-tailed. We are going to assume that the populations have the same variance and standard deviation. Now, that F statistic is actually a ratio of the variance between the samples and within the samples, and I'm quickly going to go back to my results. And here we have our degrees of freedom. This would be 1 in our numerator, 1 in our denominator. On our results page here, this top number is our variance between the samples, and the bottom number is the variance within the samples. And this ratio, so 1,011 divided by 248, is where we get our F statistic, and you'll see that on the next slide. So the variance between the samples and the variance within the samples, and that's found on your printout under this MS. So that is what you want to look at, and the way that it's on the table is exactly divide the top number by the bottom number and you'll get your F statistic. Now I do want to talk a little bit. Here's our degrees of freedom in our numerator, our degrees of freedom in the denominator, and this would tell us how to go to the table in the back to find our critical value. I just wanted to point this out. We are not going to use that table. How are we going to do this? If all the sample means are close, that means we get a small F statistic and a large p-value. So our F statistic would be in this larger part of the distribution, and we would fail to reject. If we have at least one sample mean that's very different, our F statistic will be large, and so we'll have a small p-value, so we will be able to reject. When we do this, we are not going to do t-tests between the samples to see which ones are different. When we do that, what we have to do is we have to put in a correction term so that we adjust for type 1 error. That's what's covered in the second section of your textbook. You can read that if you're interested. If you look on page 649, you will see the results, and if you were going to do a study, you would get a results like the one in the middle of page 649, and then using that information you could see which of your means actually are different. Let's actually look at the data that's in one of the sets that came with your book, and it's data set 5. I just opened it up in StatCrunch, and I want to look at the lead levels in this row, and I want to look at the IQP. Now I found this because I compared this data set to the table that was in your book, but I just want to show you how you would do this. I'm going to do stat ANOVA one way, and my values are in a single column. So my responses were in that IQP column. And then my factors, my lead levels, are in the lead column. And this is where I would do compute. And that's how I got my results table that I talked about in the slides. Now I want to show you something else that you can do, uh, and let's look at a little homework here, or a problem out of the textbook, so you can see how you deal with the data. Let's look at number 5 from your homework, and we'll work through it because I want to show you what you need to do in StatCrunch to make this work. So first of all, we're going to determine the null hypothesis and alternative hypothesis. And so not your statistics instructor, but another one participates in triathlons. And we have tables with his time in minutes for each of 5 laps through the mile. And then we're going to test that to see if the means are the same. So our null hypothesis is going to be that all the means are the same. And our alternative is going to be at least one, not exactly one, and we don't do the not equal to, not equal to, not equal to. There's just one that's different. And then we want to find the F statistic. So that's where we're going to use our table, and we're going to go to StatCrunch. So here we go, and I want to open this in StatCrunch, and this is a crazy one because they do the table stupidly. So let's look at this. This is the minute and this is the seconds, and to be honest with you, I think this is really dumb, but let's try it and see what we come up with. I want to do something with the data. I want to stack it. So I want to go to range, stack, and let's just do the seconds columns. So I want to do seconds, and I'm going to do control click to get my mile 2 seconds, and I'm going to do control click to get my mile 3 seconds. And I want to store the labels in mile. So I'm just going to do a mile. And I'm going to do compute, and you can see what has happened to my table is here I have my labels and here I have the seconds. Now I was able to do this because all of my minutes were 3, so it was just the seconds that were different, and we'll keep our fingers crossed that this works. So now I'm ready to go to Stat ANOVA one way. I want to do values in a single column. My responses are in that variable 8 column, and my factors are in that mile column that I set up. And then I'm going to do compute. And so here I have my mean, here I have my F statistic, and here I have my p-value. Let's go ahead and see if this works as we go through and we do our problem. My F statistic is 22.3062. That worked. And then my p-value is 0.0001. Now, my p-value is very small, so that means I can reject, and when I reject, there is sufficient evidence to warrant rejection. And does one of the miles appear to have a hill? Let's go back to my data set in my stat lab, and notice that my mean time is about 10 seconds more on mile 3. So I'm thinking that mile 3 is going to have a hill. So let's go back here. First mile appears to take longer. No. Does not suggest any of the miles have a hill. No. These suggest that the third and first. No. These suggest that the second takes longer. No, it's the third one that takes longer. And so that's how you would do a problem like that. So I just want to review a little bit. When your data comes up and everything is in columns, you want to stack those columns, and then you put the header to the column in your label column so that you make two more columns, and then you'll be able to do your ANOVA using the data. Or you could, you could put it in again, but it's easier to do the stacking.